Hello everyone, and welcome to the fifth video in this series where we create a custom environment for deep reinforcement learning as applied to portfolio optimization. And as always, if you're new to this video series, please go back and look at the other videos in the playlist so this will make a little more sense. In this video and the next actually, I'm not quite sure of the best order, because here I'm going to describe the actual model, which is a very low level component of the reinforcement learning algorithm that we're building. And in the next video, I'll kind of go back and look at the high level algorithm itself and how it comes together. But I thought it's worthwhile maybe to start at the model because there's some aspects of the model that I think are very important and relates very much to the environment that we're working in. So to do that, what we kind of do is step back and look at the signals that the model must, and the model, when I say model, it's really the artificial neural network that we're building, right? And so we looked at the information that's coming into it, and so we're not just going to make any generic sort of model. We want to try to tune the architecture of that model to kind of match our task. And so if we look at the synthetic price history, which was developed to try to emulate the real price history and the relationship to the signals, there's two things that we notice right away. One is that when we created it, we brought in this dependence on previous history, right? So basically this is not a Markov process. So the change in the price is not just a function of the current signals, but also previous signals. We have these first and second derivatives here that look backwards in time. So because of that, we want to be able to have a model that's not just looking at the current set of signals, but the previous signals as well. And that's something that we're actually, proposing that is real. However, if this is something that you did not believe, then it wouldn't make sense, first of all, to create these signals based on these derivatives. And also when you create your model, then you probably would create your model differently. So for us, because we believe there is some of this history in the data, and of course we kind of know because we're creating the synthetic one, but more importantly, when we go to the real one, there is a belief that there is a bit of history in the data. What we do is we start our model with some sort of feature that can capture that time history. And what we're choosing is a convolutional neural net, a 1D convolutional neural net, or CNN, to ingest this data. So it looks back over a time window, which is a hyperparameter we can tune. And then within that time window, it has a kernel that slides across. So for instance, we have a time window of 10 days. So at every single point in time, it not only looks at the signal at today, but the previous 10 days as well. And then the kernel kind of slides along. It's a day of 3, for instance, and that kernel size will slide along all those call them 3-day tuples as you move back to kind of pull patterns out of the data. So we'll start off with our model with a CNN to try to capture this data. And then the second thing we look at is when we look at these signals, we can see, for instance, this is the simple moving average, 20-day simple moving average for this particular asset. And then there's, the priced earnings of that same asset. And overall, there is, again, remember 11 for the days of the week, so 60 total. We have 10 assets, so there's 6 signals for each asset. And these signals are actually normalized as well. And because of that normalization, especially, we wouldn't really think that the performance of this particular asset would be very dependent on this particular signal. So because of that, we don't want to just ingest all 60 signals into our network. We want to kind of divide up the signals by asset and then kind of feed it into its own mini network. But then at the end, when we go to trade, we kind of have to bring it all together. And there's actually an issue here, and because this repo is definitely a work in progress, I would suggest that you have a look at the issues. Every time I kind of want to do one of these videos, I find other issues. I just make it, capture it here. And also, if there's something that you do find, please go in and raise an issue. People can raise issues, and I will be more than glad to kind of go in and have a look. For this one, this is where I want to make it sparsely connected. And what I mean by sparsely connected is that all of those 60 inputs are not fully connected to the network. There's actually a good paper that I have listed here, which shows kind of how you could break that up into all different types of ways, right? So for us, they kind of have 3 groupings, and for us, it would be like if we had 3 assets, right? And they also have 3 subsignals. So for us, if we had 3 signals on 3 assets that would be passed in, and then you would kind of learn just on that independently, and maybe And this was actually even do a higher level grouping. So you can see you can group and group and group. And there's many different ways you can make the connection. So I usually say fully connected. So a fully connected network, this node would be connected to this, this, and this, right? And if you went all the way, you would have to go down and connect over and over again. So this is a kind of a good idea that there's many ways that you can kind of do this. Actually, this architecture is probably the one that's closest, where it kind of sum together. And if I go back to, if I go back to the issue again, because we're doing this PyTorch, I was kind of reading through. There was someone had a similar sort of problem that kind of aligns with us. In the final report, I'll have a prettier picture kind of replicating ours. But I think for here, it kind of still gives you the idea where they have 3 of these little mini networks. And so you have a network for each asset. And in this one, you have 1, 2, 3, 4, 5 signals, say, coming in. So we would have 6 signals for each of the 10 assets coming in. Now, this one is not a CNN, but we would simply have a CNN at the beginning of this. And then we kind of do some a fully connected layer here on top of the CNN to kind of bring this together. And then at the top, you bring it, and here they have just another layer that tries to capture the connections between each of them. So you kind of have another fully connected layer out here that bridges all of these sub-networks together. And in this particular one, I think he's doing a classification. He just has a single node. But for us, because we have 10 possible assets, we have 10 assets, so we have 10 possible actions, buy and sell on each of the assets. The final set of nodes here will be 10, right? Because here it's basically saying whether I should, for this particular, let's say this was asset 1, we kind of have a subnetwork, we bring it all together, right? We'd have the connections across, and then it spits out for this particular asset, do I want to buy or sell? So that node would be a buy and sell quantity. Or actually it is the desired weighting, and then you have to compare with the current weighting to determine if you need to buy or sell, right? So this is an idea I thought I kind of would show here before we really dig into the meat of the algorithm, because it's kind of how we structure the low-level model. It then influences how we put together the larger model. And I think it's a great illustration of where if you just go in and hit your data with a very large network and we just connected all 60 inputs, with enough training, it probably would have realized that a lot of the nodes would have a weight of near 0. And effectively what we're doing here is we're nulling out all those. So instead of connecting this node, for instance, to all of the possible nodes, right, you can imagine every line is a weighting. You could learn it so that these are effectively 0, or here we've just disconnected them, right? And that's the idea of being sparsely connected. So that's a basic idea of how the model was built. Again, we're starting at the beginning with a convolutional neural net, and that is to try to capture some of that time history that we have in here. Again, we're assuming that the efficient market hypothesis is not holding true. We don't have all the information required on the current state. It's a non-Markov process because we're looking back through time and using the signals in the time history to kind of predict what we should do going forward. So I think that's it. I'm going to cut this video off and start in the next one. I just want to have a little bit of a primer really for the next video, showing the type of model that we have and why we picked it. So in the next video, we'll kind of go quickly over the model shape with this current background behind us. Okay, thanks, and I'll see you in the next video.